So with that, let me introduce our first speaker, who's Gernant Maurer. He received his BS from my university, Johns Hopkins University, and a PhD from RPI. Gernant served as a Vice President of Technology at Special Metals Corporation, a leading supplier of high-performance nickel alloys in New Hartford, New York. In 2003, he joined Carpenter Technology Corporation as the Director of Research and Development and has been involved with new product and process development for specialty alloys until he retired in July of last year. Gernant is currently the Vice President of ASM. He just told me that to be Vice President, you have to retire from your day job first. So he's Vice President of ASM, and he was a founding Vice President of the Specialty Metal Processing Consortium, which is a unique effort that allows industries to jointly fund proprietary research in conjunction with government-funded laboratories. So, Gert, the floor is over there. I'll go right.
Good afternoon, and thank you all for participating today. In my 10 minutes, I hope to give you my perspective of 35 years in the specialty alloy industry, designing materials and making materials for aerospace, defense, and many other industries. Before I jump into that, though, I want to do a couple things. First of all, I just love reminding people that materials enable technology. And it also defines civilizations. Whether it's the Stone Age, Bronze Age, Iron Age, we're now in an age that I called integrated materials age because we have all these incredible materials innovations that we integrate into things like the Dreamliner. On the right is the smartphone. I call that our children are wasting 10 hours a day texting age. But that smartphone that Kevin showed us, I always remind kids when I talk to them that smartphone was made from a pile of rocks. Think about that. That's materials innovation. That's what we're talking about is accelerating that process of taking rocks and turning it into incredible materials that can drive our economy and our lifestyle. The second thing I want to do is give you a 60-second lesson on computational modeling, because some of you are familiar with computational modeling, some are probably fuzzy, and some would probably know nothing. I take an example away from the specialty alloy industry, and we call it thermomechanical processing. Blacksmiths call it heat 'em and beat 'em. But on the far left is an ingot, maybe a 10,000-pound ingot of nickel base or titanium alloy, and the engineer wants to come up with a simulation to learn how to process that ingot to get the size and the metallurgical characteristic that he's striving for. So the first thing he does is on a computer, he'll take those geometries and create simple shapes on the computer. There's the ingot and the forging die that you'll be deforming the material. And from that geometry, on the right, do something called meshing. And all meshing is that you take that geometry and you break it up into tiny little pieces. We call them finite elements. And that's where computational modeling comes in, because each of those finite elements, you write a set of equations. This is the last differential equation I'll give this afternoon. And you set up boundary conditions, and you use a computer to go through millions of iterations of solving equations so that each finite element meets certain boundary conditions next to each other. And over a period of time, you can simulate the actual deformation process from equations that describe the physical changes that are occurring. I put in red there, that equation's nice, the computers are nice, but unless you have lots of very, very, very good data, all your results are meaningless. You always come up with pretty pictures, and all this is a result of a simulation. The color coding could be temperature, could be metallurgical structure, it could be accumulated deformation. But that result is only as good as the data that you put into it. And as the old adage goes, garbage in, garbage out. And one of the topics we'll have today, how important it is to generate an infrastructure where there's good data available, that many people can access it and get good results. Back to the specialty, that's your 60-second course there. Back to the specialty alloy industry, we use computational modeling at all levels. If you were to tear apart a jet engine and look at the most critical parts, this is a nickel-based superalloy at a very high magnification. They're complex materials, complex alloys, lots of phase interactions. The phases you see give incredible strength and service life to jet engines. That's one application of the computational modeling. That's usually the easiest part. The next more difficult part, and something I spent 35 years doing, is figuring out how to make that alloy in production, scale it up from a laboratory 10-pound heat to a 30,000-pound heat. And you go through modeling for melting and casting, which is shown up above, and down below through thermomechanical processing. In addition to, well, part of the output you get from solidification, this is an example of modeling that you do on ingots. These are full-size ingots at different diameters. These could be 10,000-pound ingots of metal that's solidifying, understanding the solidification that's going on so you get the structures and you avoid defects that are so critical in aerospace materials. That's on a macro scale. We also dive in deeper in solidification on a micro scale, and this is dendritic solidification, solid growing into a melt. We look at this detail and these very complex alloys and look for segregation and phase stability issues that it may result. Always pretty pictures, though. Especially alloy computational modeling world is that we use computational modeling throughout our processes. But each of the processes, whether it's alloy design, melting, solidification, they're modules. We do modeling on a very specific problem, and they don't talk to each other. Especially alloy producer would go through this sequence, and then we would send it off to a customer who then would forge it, heat treat it, machine it, and then eventually create the component. The real key to this talk today and our discussions that we're going to have is integrating each of those modules. When you see ICME, that's what it's all about, especially metals industry. Having the models talk to each other, it's integrating all these different modules so that they build upon each other, and you can do the development at a much quicker pace. So you take, there's your alloy design, but when you do alloy design, you should understand the solidification that's going to be going on, the mechanical properties, the stability, and even all the way down to the service life in the component and then the total cost of the system. All that can be simulated. That used to take 10 years to do. And usually got to the end of the 10 years it didn't work. So now you can do that in a week. Just think about the power of that, to be able to integrate those tools. It's all about materials innovation, making materials better, but making them quicker and cheaper. And in a competitive world, the person who does it better, quicker, and cheaper is going to drive the economy, the world economy, and drive the next generation of technical innovation that are going to use those materials. I put together this schematic just to illustrate a point. It's a plot of impact versus time. And probably the most mature of the modeling capabilities that we have in our industry right now is thermomechanical processing. It started back in the 70s, and it started at Air Force Materials Lab and a bunch of other national labs. We did a tremendous amount of work when the software was originally developed. Computers were slow then, and it matured quickly and is used throughout our industry. The second would be solidification, and alloy models are just starting to take off. We're getting some benefit from them now, but we're just at the beginning of that. The key to this slide is the dotted line, and it's the integrated computational modeling engineering line. And the entity, whether it's a country, business, probably the competitive world, the person who climbs this line the fastest, has the greatest slope, is going to have a tremendous advantage in the world of industry. Final slide is my scorecard. We've done a terrific job developing software at our universities and national labs. Our computational speed is incredible now. You need a tremendous amount of speed to drive these models. Typically, a thermomechanical model can run from anywhere from 15 minutes to a week. So if you can shorten that time by an order of magnitude, you can imagine the benefits of that. The data, though, getting the database to drive those models is a big red light. And I hope we get a lot of discussion about that today. If you don't have good data, it's very expensive to accumulate. When people do spend the money to accumulate it, they keep it a secret to themselves. That's a real drawback and something where we could build an infrastructure in this country. The last scorecard is on people. Shame on us. It's a double red. We've totally failed in producing the amount of science, math, and engineering technologists to drive our economy. And I hope we're able to discuss that today. We have some of the best universities in the world. We unfortunately can't fill them with our own students, so we fill them with the brightest, smartest and brightest people in the world. Come to our university, they get the best education in the world, and they leave. In the old days, they stayed. They contributed tremendously to our economy. But now they're difficult. It's difficult for them to stay, and it's difficult, and they have reasons to go back to their homelands and take those tools back with them. Up to 70% of our top graduates are foreign nationals in engineering, and they leave the country. That's all I have to say.
Okay, thank you, Gert. So again, we're doing